All right, let's just dive right into this explainer. Today, we are going to totally demystify exactly how the internal workings of your computer's central processing unit actually operate. You know, we use our devices every single day, seamlessly tapping screens and typing on keyboards, but how often do we actually stop to consider the incredible microscopic choreography happening right under the hood? Well, today, we're unpacking the CPU, the undisputed brain of your computer.
I mean, it honestly feels like magic sometimes, right? But as we're going to see, computing magic is really just highly organized logic and rapid data movement. When you ask a computer to perform a complex task, it isn't thinking in the human sense at all. Instead, it relies on these intricate combinational circuits made from logic gates. It literally takes these monumental, complex tasks and breaks them down into millions of tiny, incredibly fast logical steps. So, here's our game plan. We'll start by checking out the core components, map out the bus system, compare RISC versus CISC architectures, walk through the fetch and decode cycles, and finally wrap things up with cache memory levels. Let's get to it.
Part 1. Core Components. Let's meet the main cast of characters inside your CPU. A great way to think about the CPU is to picture an ultra-efficient, highly synchronized commercial kitchen. First up, you've got the Arithmetic Logic Unit, or the ALU. This is your master chef, the absolute workhorse that performs the raw arithmetic and logical operations on the data. But a chef needs someone to read the tickets and manage the whole flow of the kitchen, right? That is our control unit, or CU. The CU manages instruction processing, interpreting everything via decoders, and strictly controls the data flow between all the other components. Then we have our registers, things like the program counter and the accumulator. These are small, extremely high-speed memory locations. Going back to our kitchen analogy, these are basically the cutting boards sitting right in front of the chef, holding the exact ingredients being processed right this second. And finally, we have cache memory. This is a smaller, faster memory stash located right near the processor core, kind of like a nearby pantry, which drastically reduces data access time.
Moving on to part 2, the bus system. Basically, the information highways of the CPU.
Looking at a classic one-bus system architecture, it's pretty amazing how everything connects. You can see the general purpose registers, the program counter, the instruction register, and the memory address and data registers, all physically linked together along this one shared primary pathway called Bus 1. It's also perfectly set up so the ALU can grab data from register A and register B, process it, and immediately drop it right back onto that bus. It's just an absolute masterpiece of digital plumbing.
Now, not all of these pathways are doing the exact same job. Take the data bus, for instance. This is the literal two-way street that moves actual data from one part of the computer to another. It can flow from the CPU to memory, or from memory right back to the CPU. And just like a physical highway, capacity is everything. The width of this bus dictates exactly how much data traffic can travel at precisely the same time. So a 16-bit bus, it can transmit exactly 16 bits of data all at once.
Of course, to keep that busy highway from turning into total gridlock, you need a traffic director. That's exactly what the control bus does. Instead of carrying the raw data, this bus transports precise orders and synchronization signals straight from the control unit out to all the other hardware components. It's also bidirectional, which guarantees that control signals and acknowledgements can seamlessly ping back and forth between the CPU and memory.
Part 3. RISC versus CISC. Let's talk about instruction sets.
Literally every single thing your computer does, from opening a simple web browser to rendering some high-end 3D graphics, is ultimately broken down into instructions. These are your fundamental machine language binary codes. The processor's whole job is to fetch, decode, and execute these binary instructions to perform operations like basic arithmetic, data movement, and control flow. All of this is defined by what we call the instruction set architecture, or ISA. But here's the catch. Different processors speak slightly different dialects of this binary language. So this leads us to the big showdown between two completely different design philosophies, RISC and CISC. RISC, which stands for Reduced Instruction Set Computer, prioritizes a very small and simple instruction set. These instructions are fixed length, incredibly efficient, and usually take just one single cycle per instruction to execute.
Because the commands are so simple, RISC architectures need more general-purpose registers to juggle temporary data. On the flip side, we have CISC, or Complex Instruction Set Computer. CISC uses a large, complex set of variable-length instructions, meaning one single instruction might execute a whole multi-step operation. Take the legendary 8086 microprocessor, for example. That 16-bit CISC chip completely revolutionized computing with its dedicated complex execution and bus interface units. And because CISC handles so much within the instruction itself, it actually needs fewer registers than a RISC design, two completely different ways to solve the exact same problem.
Part 4. Fetch and Decode. This is where the real action sequence happens.
It all kicks off with the fetch cycle, which is basically a lightning-fast relay race. Step 1. The address currently in the program counter gets transferred over to the memory address register. Step 2. The control unit fires off a read signal to the memory. Step 3. Memory replies by grabbing the specific instruction at that address and dropping it into the memory data register. Step 4. That instruction quickly moves into the instruction register so the CPU has it locked and loaded. And finally, Step 5. The program counter increments, pointing it straight to the very next instruction. And get this, in modern CPUs, a technique called pipelining lets the processor fetch a new instruction while it's simultaneously decoding and executing others, which massively speeds up this whole race.
Immediately after that fetch cycle, the decode cycle begins. With the instruction safely sitting in the instruction register, the control unit acts like a master translator. First, it checks the opcode part of the instruction. That's the specific chunk of binary that says what action needs to happen. Next, it figures out the exact operation to perform based on that opcode. Finally, it identifies exactly which operands or registers are involved. It's turning a coded message into a concrete action plan. Now, obviously, doing this at lightning speeds can cause a few hiccups, what we call data or control hazards. But modern processors are smart. They cleverly manage these traffic jams using techniques like pipeline stalling, operand forwarding, and branch prediction. And finally, Part 5, Cache Memory Levels. These are your CPU's built-in performance enhancers.
When it comes to cache, it is literally all about location and speed to keep those fetch and decode cycles moving. Level 1, or L1 cache, is the absolute fastest. It's super small, but it's embedded right on the processor chip, closest to the CPU cores, holding the exact primary active data the core needs right this millisecond. But what happens if the data isn't there? That's an L1 miss. When that happens, the CPU checks the Level 2, or L2 cache. It's a little further away from the cores, so it's a bit slower, taking about 10 nanoseconds to access. But it makes up for that by being larger, usually between 256 kilobytes and 2 megabytes per core, acting as a crucial backup for anything L1 missed.
And backing up that L2 cache, modern systems usually pack a Level 3, or L3 cache. This is your final vital layer of on-chip memory. It dramatically reduces those L2 misses and acts as the ultimate safety net before the processor is forced to trek all the way out to the incredibly sluggish system RAM. Plus, in modern multi-core systems, while L1 and L2 are mostly dedicated to single cores, this massive L3 cache is generally shared across multiple cores working in parallel, requiring some really brilliant traffic management to avoid contention. So when you put it all together, the buses routing traffic, the registers holding immediate data, the tiered caches optimizing memory delivery, and the relentless sequential fetch and decode cycles, you see the truth. A CPU is not magic. It is, without a doubt, the most meticulously organized, flawlessly synchronized factory on Earth, quietly executing millions of logical steps every single second to bring your digital world to life. The next time you click a button, stream a video, or just type a single key, I hope you take just a brief moment to appreciate the absolutely incredible microscopic journey of the instruction you just fired off. And I'll leave you with this final thought. Sitting right there in your device, humming along perfectly right now, what will your CPU fetch, decode, and execute next?